Welcome back, everybody. So this is the third section of Chapter 8. Section 1 of Chapter 8, we looked at gases. The second section, we looked at intermolecular forces. The third idea here in Chapter 8 is physical properties, basically physical properties of solids and liquids. So here's our first experiment. Now, hopefully you looked at the video, the animation, at what the particles are doing. So here we can look at vapor pressure on a macroscopic scale. So go into a 7-Eleven and get a Slurpee. Dump the Slurpee out. It's not a healthy thing to drink. But here's the experiment we're going to do. I'm going to go to the bottom of the page here. I'm going to take that Slurpee cup lid and I'm going to put a pressure gauge on it. So that's going to measure my pressure. And there's my Slurpee cup. Now let's see, I'm measuring 752 millimeters of mercury. Now the second thing I'm going to do then is I'm going to take that Slurpee cup and I'm going to pour some water into it. I've got my cup right here, my pressure gauge, 752. Then what I'm going to do is quickly just put the lid on. There's my pressure gauge. Now, I'm not going to squeeze the cup. I'm not going to heat the cup up. All I'm going to do is pour the water in and then quickly put the lid on it. And it goes to 775 millimeters of mercury. Now, I didn't squeeze the cup. I didn't add anything to the cup. All I did was pour the water in. You can see it was at 752. All I did was put the lid on and it jumps up to 775. So the question is, why did it jump? What is that little increase there? Well, remember, of course, we have evaporation going on. If you remember what the particles were doing, I have some evaporation. And what happens? Well, those particles end up here bouncing around, those water molecules. And that gives me some vapor pressure. That's lousy handwriting, but you can see it. So vapor pressure, we usually say PV is vapor pressure. So there we go. Above any liquid, there's always some particles that are escaping, and it gives us vapor pressure. Now, if we think back to the kinetic molecular theory of gases, the pressure is related to, if we put more particles in, pressure goes up. If we increase the temperature, the pressure goes up. Now, let's look at the next page. Let's look at water. Now, what I've got is, here's a temperature, minus 20 to 100. Here's water, and it says, as we would expect, the vapor pressure of water goes up, 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 more and more steeply like that. That's because, of course, the particles are escaping. Higher temperature, the particles in the liquid are moving around faster, and more particles are able to escape and produce a vapor pressure. So you can imagine I've got this beaker over a Bunsen burner. And I got a flame, nice flame. And I'm heating that thing up. As I heat it up, more evaporation occurs and I get greater vapor pressure over the top of that thing. Well, one thing we don't think much about, but there is air pressure. We could say atmospheric, or barometric pressure around us all the time. So there's this barometric atmospheric pressure. So that's kind of our image of what's going on. Let's think about this. It says as the temperature increases, what does vapor pressure do? Well, it goes up. If you increase temperature, you get increased vapor pressure because more particles are escaping, more particles are evaporating, and they're moving faster. So we will say liquid particles escape to become gas particles. That's what's going on. Now, let's look at this again. If we go back up here and say, well, gosh, it goes up and goes up and goes up. And let's think about what that atmospheric pressure was. Let me get a red pen here. Let's do this in red. Well, here's atmospheric pressure. Right there. I'm just drawing a line that says, gosh, right there when the vapor pressure of water hits the atmospheric pressure, what it sort of means is the vapor pressure, PV, is equal to atmospheric pressure. Well, let's see what the temperature is when that happens. I say, okay, well, pressure goes up, goes up, goes up, hits atmospheric pressure. Let's come down here and see what we've got. 100 degrees. At the boiling point, the vapor pressure has gone up high enough that it's equal the atmospheric pressure. And what do we observe? Well, the gas bubbles start pushing their way out of there. So we'll say normal boiling point is when the vapor pressure, the normal boiling point is when the vapor pressure equals the barometric pressure or the atmospheric pressure. Let's say barometric. Now we say normal boiling point. That means at 1 atm. Normal just means 1 atm. At sea level, that's about what the barometric pressure is. Now, what's going on? We talked about this a little bit when we looked at the particles. What are the particles doing during vaporization? Well, remember, they have to escape. There's some liquid particle, let's say liquid particle IMFs, right? That's what's holding the particles together. Well, we have to break that. We have to add some heat to turn them into gases. Gas phase, there's no interaction, there's no stickiness. So we had to break these. What did it take to break that? This heat of vaporization, delta H vaporization. I have to add a certain amount of energy in to break these up to turn them into gases. So big ideas. Boiling happens when the vapor pressure reaches barometric pressure. We start seeing the bubbles escape. And that heat that we were adding in up here, it raised the temperature, and then ultimately that heat had to break up the liquid particle IMFs. Well, let's look at that, maybe a couple more sketches on page 819. So let's think about melting first. I'll draw a perfect beaker. Here's my solid. Particles. There's my solid. I'm going to add heat. There's my beaker. Got all in there, yeah. Now, they're still mostly connected, but not exactly the same. So I'm going from my solid to my liquid. And what I'm doing then is I would argue that I am breaking. Did the light just change? I think the sun's coming up or something. Oh, that still looks good. Breaking the solid particle IMFs. We're breaking apart the solid intermolecular forces. Not all of them, but to some degree we're breaking them up to allow it to become the liquid. Maybe I'll put a few more particles in there. It looks like a little better balance. Now that energy required to do that is basically the heat to melt. Now we don't call it the heat of melting, unfortunately. We call it the heat of fusion. I'm going to say heat to melt. And we call that the delta H. It just means a change in enthalpy to get it to melt. It'd be nice if we put a little M there. We call it fusion. So that's the energy to take the solid to a liquid. It's the amount of energy required to kind of break up some of those solid IMFs and allow, well, break up some of those solid IMFs. Not completely, but mostly. Well, then let's look at what are we doing if we're going from my liquid to a gas. I drew 20 circles there, by the way. So same thing, I'm going to put heat into this thing. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. There they go. It's crooked. Well, I'm going from liquid to gas. And now I'm breaking all the IMFs. I'm going to break the liquid IMFs. I'm going to break these things up completely. Here there's some IMFs holding them together. Here there's nothing. There's nothing holding gases together. Well, we might think of this as evaporation, vaporization. So we call this the heat of evaporating. Let's think of it as that. Heat of evaporation. Evaporation. Well, we call it vaporization. So the symbol is delta H. It's the difference in heat. How much heat energy do I have to add? And I'll put a little V for vaporization. Makes sense. Oh, yeah, that's right. Well, solids sticking together, you better add some energy to break them up into a liquid. Liquids are sticking together. You've got to add some energy to turn it into a gas. Heat of fusion, heat of vaporization. We might even say enthalpy of fusion, enthalpy of vaporization. Well, let's look at some numbers here. This is where it gets, well, it's all, I was going to say, this is where it gets interesting. But it's all interesting. I love this stuff. Okay, here's my experiment. I take an 18-gram ice cube out of my freezer. I found out the average in those crappy little trays, about 18 grams. Take an 18-gram ice cube, and I have something set up to deliver like every minute or something, or every second. I don't know what my time is. 200 kilojoules, 200 more kilojoules, 200 more kilojoules, 200 more kilojoules. So I stick my ice cube in there, minus 10 initially. Boom, minus 5. You know the next number, 0 degrees C. What would you predict for the next number? Stop the video and say, oh, I know what the next number would be. All right, did you stop and make a prediction? 5, 10, 15, right? How about this? 0, 0, 0. I keep adding energy, but there's no change in temperature. So you say the two words often said in the laboratory. You say, oh, shucks, or some other word. So you're watching this thing, you're adding 1,000, 5,000, 6,000 kilojoules of energy to this stupid thing. 0, 0, 0, 0. And finally you get somewhere nearly 7,000 kilojoules and you start to see the temperature go up. And it marches up steadily. 3, 6, 9, 12, etc. 96, 99. Everything seems okay. Everything seems fine again. I'm adding energy. The next temperature you would expect. Stop the video. What's the next number and the next number? You probably predicted 102, 105, 108, right? So I get to 100. I think, well, okay, at least it's still going up. Maybe the next number will be 103. And the same thing, 100, 100, 100, 100, 100. And you're thinking, wait, what is going wrong with this experiment? I am steadily adding heat to this thing. The temperature goes up, then it plateaus. Goes up, plateaus, goes up. So, of course, you're saying the two words. So you go back and start looking at your notes. And you go, well, why don't I look and see what was going on here, 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 here. Well, here I had ice. Just an ice cube. But here I noticed, well, wait, I had ice plus water. Oh. Then I had just water. Now let's think about this. What was going on? I had ice, temperature went up, then I had ice and water, and as I'm adding heat, what was happening to that? Well, the ice was melting. Oh, this energy right here, there's my delta HF. Let's put 3 exclamation points. I was adding energy in. It was not raising the temperature. It was breaking up the bonds, those IMFs. When all the ice was melted and I just had water, I get a change in temperature. Then I notice this. Here, I've got water and steam. What's going on there? Delta H vaporization. I'm adding energy in, but it's not increasing the temperature. It's only breaking up the IMFs for the liquid. And finally, I get here, and I just have steam. So a couple things to note. During phase changes, I should have done that in red. During phase changes, delta T equals 0. Look at that. Melting, 0 degrees, no change. Boiling, 100 degrees, no change. So during phase changes, delta T is 0. The delta H, that energy I'm putting in there, is just breaking IMF bonds. IMF, well, bonds, they're not bonds, but wow. Cool. One last thing. Let's jump to page 8.25. Here we can see it graphically. You can imagine what I'm doing is I'm just adding heat, 1,000, 2,000, 3,000, 4,000 kilocalories per mole. And I just steadily keep adding this thing, some kind of machine. And I'm noticing the temperature. I go, well, okay, first I've got a chunk of ice. I'm adding energy, goes up. Then all of a sudden, despite the fact that I'm adding energy, the thing just levels off. Then keep adding energy. Oh, it seems to be behaving again. And then here, for a long time, I'm adding energy. 4,000, 5,000, 11,000 kilojoules. This levels off. And finally again, oh, now it's going up. Well, what's going on here? Boiling. What's going on here? Melting. We see like, oh, I'm adding energy. The energy is not increasing the temperature. The energy is merely breaking up the IMFs. So here I've got water. And as I add energy to water, way back chapter 1, you add energy to it, temperature goes up. Here I've got ice, and here I've got steam. Now, if we weren't in this crazy situation, we could do a whole bunch of math and stuff, but we're not. We're just going to do this very conceptually. Okay, so we talked about IMFs. Now we talked about physical changes, physical properties. In the last segment in chapter 8, we get to do the coolest thing. We get to connect IMFs to physical properties. And now we get to make all kinds of predictions. I love this stuff. All right, guys, I'll see you at the last section, last lecture set for chapter 8, which I don't have the page in front of me that it starts on, but you'll see it when we get there.